Okay, so we'll continue on linear prediction. So we'll finish our linear prediction today, I think on Thursday, the BTA session. I think Thursday, yes. Okay, so let's do a little recap on linear prediction model for speech. And this is a basic idea. So the basic idea is trying to find, a modeling means basically finding a mathematical way or a mathematical function to model the speech signal. Model meaning it's represent as speech signal. Okay. So there's approximation. A speech sample at time t can be approximated by the linear combination of passive signal sample. It's a very intuitive idea. Right? Every sample in the time domain particular point is a summation from the past p points with their associated coefficients. So the relationship to the source and filter model that we know about the speech production is linear prediction can provide a robust and reliable estimate of filter parameters. It's also a very widely used technique for estimating pitch, performance, and the rest of speech production. Okay, a lot of application exists originally in speech coding, okay, or the terms we call it compression. So by representing speech signal as a set of coefficients, you effectively reduces the number of bits you need to store the speech. And then the LPC can also be used for various front end. Okay, so the idea is that the simple hypothesis, right? Every single point in time, okay, is a linear summation of the past p points. So k from 1 to p, with each of these some coefficients, plus some error function or some input function. Okay, so again, repeat as we look at this equation, the basic underlying assumption that we engineers make is this point is a linear summation of the past. Okay, that means there's very high correlation between your neighboring points, right? This particular point is simply some versions of past samples, sum it up to be the current sample. Okay, so and it continues to roll, right? So the next sample will be the past p sample, the next sample will be the past p samples. Okay, so what here we're trying to say, okay, every single point here is not, they're not independent. Okay, it has very high correlation or structure with the past p sample, and which is a very intuitive idea we can think about speech because we're speaking in sequence, things have relation with respect to one another at every single frame. Okay, so that's a basic assumption, difference equation for linear prediction. Okay, so what's the linear predicted signal is just this, right? Sum from k from 1 to p, right? K, p samples, each one of them with the coefficient and the delay of the original signal. Okay, alpha k we call it prediction coefficient. Okay, I think we started last time. How do we actually get those coefficients, right? So you have a mathematical model, right, of the speech signal, which is the linear predicted signal. Okay, by taking the past p sample, you can reconstruct the current speech samples. Okay, so the thing that we don't know are those alphas. Okay, if the signals are being added, what are those alpha values? So there are p of them, right? Those p alpha coefficient, we call them filters. So how do we try to find those alphas, right? So you say, okay, let's define another signal, okay, called error signal, which is the difference between a real signal and the signal that we thought it should be, the linear predicted signal. Okay, so the difference between them basically Sm minus some k from 1 to p, the alpha k s minus k. So of course, you want this signal, the linear predicted signal, to get as much information about the original signal, to make the rest of the error signal as simple as possible, right? So what exactly are we trying to minimize here? So we say, let's try to minimize, okay, the short time error signal, which is the difference between the two. Okay, so the short time error signal energy, so SMM minus S delta N, and this is the linear predicted signal, original signal, the short time within a particular time segment, okay, frame it, particular window segments, and take it to the square. Okay, so if you write it out, it's this error signals energy. Okay, it's the thing that we try to minimize as we try to find the alpha coefficients, and then you do DED each of the alphas to try to find those find the equation. So solving it becomes, we call this generalized normal equations. Okay, sum from n, like n different points within your signal. Sn n minus I, Sn, each of this frame, okay, within it there are n samples, okay, so the m samples and then the shifted Sn and then these two multiplication, right? Equals to sum from k from 1 to p, the alpha k or the unknown alpha k or coefficients, sum m Sn n minus I and n minus k, or I between 1 to p. Okay, so we can rewrite this entire thing as phi n I k. If we write this phi n I k as sum over the m segments, m sample in that segment Sn n minus I, Sn n minus k, we can rewrite this equation instead of this equation, right? So it's phi n I 0 equals to k equations, k from 1 to p, plus k phi n I k, right? So phi is just this thing, right? You know I and k, right? So I and k, there are I between 1 to p, right? So for all this, the samples within each of the I, each of the k, right? Then you can sum up the values within that segment by shifting either to ith points or k delay, okay, and multiply and sum over the segment, right? So these phi and ik are just numbers. These are numbers you can compute. Some numbers equals to a summation of, some unknowns multiplied some other numbers. Okay, so there are p sets of such an equation that we can try to solve. Okay, so that becomes a p set of such equation as we try to solve p unknowns. Okay, so as the general ways we do this thing, the actual implementation wise, there are different methods of implementation. All right, the first one is called autocorrelation method. So the signal comes in. Okay, first we can assume Sn of m a frame of the signal is obtained by windowing a finite length sequence, right? So our Sn of m, right, the signal that this notation, Sn of m, right, the short segment of the signal, right, indexed by n. So effectively, it's just this thing, right? It's your signal multiplied by a certain windowing function. Okay, so if we think about that, Sn of m is a window that we apply, it's a signal we apply a windowing function on it, which make it 0 outside of the window. So those segments is 0 outside of the window. So you can imagine, right? So this is a segment of the window, and you're trying to say, okay, this sample is it's a summation of past p sample, right? This sample is a summation of past p sample. So you can imagine this error function has a particular behavior, because the first sample you're predicting 0, okay, to some values, okay. Last few samples you're predicting 0, okay, from some real values numbers, because these are the segment of signal you have. Everything outside is 0. At the boundary, right, you're trying to predict, right, a linear prediction, getting some past p sample to predict the current sample. Your past p samples are 0, okay. Now you have to basically imagine this kind of error function, okay. Using this kind of methodology will be large at the beginning and also toward the end, okay, because you're predicting from either 2, 0, or taking some values to try to predict 0. Okay, so prediction error can only be happen non-zero for this within this particular range. Okay, so large at the beginning, okay, and the end after NP samples prediction zeros or non-zeros. Okay, so we can try to see how we actually solve these equations. Okay, so we know phi and ik will sum from m to n minus 1 p, Sn n minus I, Sn n minus k. Do some substitution, so we have this phi and ik equals to m prime from 0 to n minus 1 minus parenthesis I minus k. Okay, then becomes Sn m prime, Sn m prime plus I minus k. So now we can look at this equation, right? And also recall the definitions on the autocorrelation function of a short segment of the window, right? Autocorrelation function on a short segment of window equals 0, and from 0 to n minus 1 minus k, xm plus n, w prime, we know a function, xm plus n plus k, w prime, k plus m. Okay, if you look at this thing, right? This is just a window segment, Sn of m. This is just a shifted window segment, okay, Sn n plus k. That's very similar to above. So, well, you can see that this phi and ik, right, originally is two segments that's trying to compute is exactly just Rn, the autocorrelation function on the particular time frame of I with index I minus k. And because they are indexed, right, so we put an absolute value around it. Okay, so it's Rn absolute value of I minus k. Okay, so this particular phi n phi sub n I k function that we just derived, this thing, right? A segment of the signal times a segment of the same signal with two different shifts. Right? So these two shifts are indexed by I and k. Okay, sum over the segment within them. To evaluate this thing, you can just directly compute the autocorrelation function with an index I minus k. Okay, then you effectively re-implement this phi and I k. So again, repeat. So what you do LPC, right? What you do is take a short segment of window, then start computing autocorrelation function. Once you get autocorrelation function, you have this. All right, then once you have that, right, that's autocorrelation function. Okay, so that's the linear prediction equation becomes sum from k from 1 to p alpha kr and I minus k Rn of I. Then the minimum mean square error becomes this particular point. It relates to your autocorrelation function. So look at it. This is the autocorrelation function of the of that nth frame at the 0 position. That's the largest point, right? Autocorrelation is largest point of 0. Okay, the rest of it is always smaller than the 0. Okay, minus alpha and Rn of k. So all the other autocorrelation, how similar you are to yourself, weighted by some alpha weighting is sum over all that. The difference between them. This thing will be minimized. So you're trying to find a set of alpha such that yourself similar, you and yourself are most similar, okay, and you with the rest of the shifted part has to be very similar, so that this difference is minimized. Okay, think about that again. Okay? Short-time autocorrelation function. Autocorrelation is a way to measure how similar you are to each other, to yourself. A different shift, okay, Rn of k is a measure of how you are similar to yourself as you lag yourself. Okay, so you lag p points, right? Because you are saying, I'm gonna predict myself from past p points. So you lag yourself p point to find autocorrelation function. Okay, you lag yourself 0 point. That means you are most similar to yourself without any shifting. The difference between the two, okay, is the error. Okay, what we mean by saying, okay, you are yourself. Okay, when you lag different p points, if you multiply them by this alpha, okay, sum it up, all this relationship, all this correlation, the difference between yourself at this autocorrelation point versus all the past p lagged autocorrelation points, where we multiply it by the learned parameter alpha, this thing will be minimized. Okay, so you're trying to find a set of alpha such that this entire error, okay, will be as small as possible. Okay, again, that brings back to the intuition. Why linear prediction, right? It's simple because you say, okay, this sample is a past p sample, sum it up. Okay, so there is assumption that there's a very high correlational structure in our time domain signal of my speech. And how do I find that time domain signal? You say it's a linear prediction signal. We know each one of them, if they multiply by a, by some alpha coefficient, sum it out, it'll be most similar to the original signal. How do I do that? Okay, you can solve that equation using calculus and so on. Differentiation in the end, when you're trying to solve, is basically trying to solve to get a set of alpha coefficients such that your correlation structure yourself at the 0 position versus your lagged p, where you assume past p signal will sum up to be you, that correlation will be as small as possible. Okay, the difference between that as small as possible. Okay, making sure you find a set coefficient as you sum up the past become you, that coefficient will be good enough so that your sum of the past will be like you in a sense that your autocorrelation function will be very small. Okay, so I think that's that's the sort of a mathematical intuition behind this. The rest of the thing are just tools to try to solve this kind of equation. Okay, so I feel like not as important, but you might want to know because this is actual implementation is what people do. Okay, so you can expand that formula into a matrix notation, right? Rn of 0 autocorrelation function of the frame n. Okay. Index is 0, 1, 2, p minus 1. Okay. 0 minus 1, absolute value that equals to 1. So Rn minus 1 is the same thing as Rn of 1. So you can see essentially it's basically a rotate here, rotate here, rotate here, rotate here. Okay, so this kind of matrix, we call this a Toepless matrix. Okay, Toepless matrix has a way to solve this inverse to get this coefficient faster, because these are just numbers, right? If you don't think about Lorentz-Drurin recursion, you can find other ways to do inversion. Okay, that also will help to solve this alpha coefficient. It just so happens this set of coefficient, the place in this particular manner, there is an efficient way of solving this. So we can actually do it really fast, okay, in terms of solving all these alpha coefficient. And that kind of recursion we call Lorentz-Drurin recursion. And these autocorrelation functions, they are also very fast to compute, right? Because you're just a segment of window and they shift different positions, like 1, 2, 3, 4, 5, right? So in actual implementation, you write C code, this is actually very easy to write, okay? You index the different address of each of the buffer points, and then look at both of them dot. So, for instance, it's based summation and multiplication and summation, right? Just dot and sum, right? So that's a very fast operation as well, okay? Dot sum, right? Shift your address, okay? Then you get all these numbers, So the Lorentz-Drurin recursion we also talked about it the last time, but these are just exercise, okay? These are a fast way of solving that kind of a matrix function. You initialize this E equals your overriding function at the 0 position. Let's define a term called case of I. Okay, case of I we call partial correlation. Okay, Ri. Okay, each of the I goes from 1 to P. Okay, all the P's order that you've decided, basically how many samples in the back you look at. Partial correlation, just the sum, just the Ri, autocorrelation function value at that position. Sum from j to I minus 1, alpha j I minus 1, Ri I minus j, E of I minus 1. Okay. Go from I from 1, 2, 3, 4, 5, all the way up to P. Okay. Then you take all these alpha I equals to Ki, alpha j of I equals Aj I minus 1 minus Ki, Ai minus 1 I minus j. Then we update your E sub I. Then you repeat for every I from 1 to P. Eventually, you have this Aj equals to Aj of P for all the alpha coefficients. So you can recursively solve alpha 1 and alpha 2, alpha 3, alpha 4, and alpha 5, all the way to alpha sub P, where P is the order that you do. Okay, so that's the thing we talked about last time, right? And repeat. So I want to make sure the idea is clear, so we don't lose in the mathematical notation. Let's put a model on the speech signal. Okay, speech signal is over time is some waveform. Okay, we say every single point here is a linear summation of the past P sample. Okay, is that a value assumption? Maybe. Okay, because we think speech is very sequential. Okay, every single point with the past P points. Okay, they should be very correlated. Okay, they're not the same, but they should be very correlated. Yeah. So if we make that assumption, we can say, okay, let's do it in a way to make sure if we have that particular model, sum of alpha sum k times the past P samples, we want to make sure that it captures the most information about the signal as much as possible. Okay, that's as much as possible. Okay, make that into a mathematical equation to say, okay, let's find an error function, basically the difference between the two. Find the energy of the errors between the two. Solve for it. Okay. Once you solve for it, that becomes a sort of phi and ik kind of problem. Okay, phi and ik, what's that computation? It's basically a segment of signal, a segment of the other signal, shift I and shift k. And then these two things shift for all I and all k, and computing all possible shifting between you and yourself. Right? So it's a methodology of looking at over a P shift, okay? All the combinations of this shift of yourself, how similar you are to each other. Right, so and then try to solve those alpha in a way, let's minimize. And minimize what? Okay, what we see is that the error that we minimize in this case essentially is this thing, right? It's this thing, is the autocorrelation function of yourself, okay, the 0 position, and the autocorrelation function of this segmental window where it has been lagged from 1 to P samples with the weight that you just learned. Okay, so you're trying, once you learn those alpha, plug this in, it gives you, make sure this is minimum. Okay, this value is minimum. So the autocorrelation, you and yourself, the similar yourself versus you and other lag of yourself. Okay, the difference between the two under this weighting, okay, this will be very small. This will be minimum. Okay, that's the whole linear prediction idea. Very simple. There's a correlational structure between my signal and finite model to make sure the alpha coefficient I solve so that when I multiply by the p in the samples, it's most like me in the sense that it kind of maintains the best correlational structure. Okay, and whatever is non-correlated, okay, between this frame is going to be left out in the error function, right? So that's that's kind of the idea. So again, repeating, you have this source and filter model as a one. When if you recall in the speech recognition, we say source, filter, we assume they're independent component. If you have LPC coefficient that somehow models your filter that captures the most of the linear correlation within those signal time series, the rest of them is non-correlating structure. It's going to be left out in the source, okay, which is the error function that will become a way we can use it to estimate pitch and so on and so forth. We'll talk about that. Okay. So there's another way of doing the same problem. We can say, okay, instead of looking at Sn of m as a signal that's multiplied by a window function and then carry out, like autocorrelation method of use. We say, okay, instead of windowing the signal, we can window the error. Okay, so we get a frame of an error, which is m equals 0 to m minus 1. So en squared m, right? So that's a window segment of the error signal's energy. Okay, in this case. So it means there's no restriction on the signal segment. So it is not autocorrelation. Okay, it is not looking at the signal and the segment. We're looking at the difference between the two and then take those differences as n minus 1. Okay. So this equation changes the limit on the summation. It's phi and ik and it goes to n from 0 to n minus 1. Okay. Sn minus I, Sn n minus k, where I again between 1 to p, k from n 0 to p. Do a little change of variables, n prime plus n minus I. This is phi n ik goes to m prime, okay, minus I, n minus I minus 1. Sn n prime, Sn n prime plus I minus k, where I from 1 to p, k from 0 to p. Okay, so it means to calculate phi nik, we require your Sn of p in the interval between minus p n to n minus 1. Okay, so to get an error signal, that segment, okay, to compute that error at that beginning point, you actually requires what happened in the past p samples. So you're taking into values of signal outside of the window signal of the window segment of the signal. So this phi nik, okay, is more like a cross correlation function where phi nik goes to phi nki. Okay. So your discount linear prediction function again you can rewrite as k from 1 to p alpha k phi nik phi n 0. Again, we write that into a matrix form. So again, phi n 1 1 1 2 1 3 to 1 p. 2, 1, 2, 2, 2, 3, 2p, p1, p2, all the way to pp. Okay, look at this matrix. So it's not a complete matrix, it's actually a symmetric matrix. So symmetric, okay, more like a covariance matrix instead of a topos where it's just rotating, where you can recursively compute. It's a symmetric. So there are other ways we can solve a symmetric matrix. Okay, inversion fast. Okay, so the operator is about p to k is the number of samples you look back e to the cube. Okay, if you do the Witten-Durbin equation where you do autocorrelation function, this matrix conversion can be solved faster to O to the p to the square. But again, these are just two different ways of solving the same things. Okay. So the actual steps, okay, we'll not go through, but you might have learned, okay, Cholesky composition of your matrix. It's a matrix inversion technique. Take advantage of symmetric natures of the matrix, make them into upper triangle or lower triangle form, so you can solve this matrix more efficient. And we borrow, in speech processing, we borrow a bit of knowledge on the linear algebra in terms of how we operate the matrix inversion to be able to solve a set of linear equations. Okay, so again, let's look at the original format, right? Sn originally is Sm equals to this form plus this form, right? So we know some gain function multiplied by the use of n equals Sm minus this entire thing. The error function is Sm minus sum from k from 1 to b alpha k is Sm minus k. Okay, so if we learn those things, then we know error function is just our original assumed input function. Okay, so again, this is the difference, right? This difference. Once we learn what alpha k is or nk is to equate to each other. So your g of un, okay, your input function to this source and filter model, okay, that source filter is the error function, okay, that we actually design, okay, to be the difference between the original signal and the linear predicted signal. Okay. So if energy in the error signal equals to energy in the input signal, okay, and G squared the energy between here equals the energy in here, then we have summation of this input source equal to 1. G is just whatever that energy of your the signal in the error. It's just a simple gain function. Okay, so other details. Okay, this thing can go various ways. Okay, there are also other ways of solving the same central equation. Okay, because what the problem here is essentially you just have two segments of stuff that shift each other. We're trying to solve this piece and coefficient. There are other ways called Lenz method. We're not going to go into it. It's compared to the Cholesky decomposition and the Lenz-Dilbert equation recursion. This is a much slower method. So people don't use it a lot. Okay. There's some issue of stability. Autocorrelation method almost ensures a stable filter. Can be checked easily with K's partial correlation. The autocorrelation function, like over time, it decays, it converges. So the alpha coefficient that you find can tend to be very stable. Okay. So if you care to use this alpha coefficient as a way to resynthesize speech, you might want to use autocorrelation method as a way to derive those alphas. Okay, again, this combining the ideas of this alpha coefficient are essentially coming from autocorrelation. Autocorrelation function is a very well-behaved function. Okay, over the index, things decays. Okay, index go longer and longer, eventually will decay to 0. Okay, so whatever thing you do to it, any transformation, anything you operate on this. And then the alpha coefficient you're also deriving from this autocorrelation function. So that alpha coefficient is your filter coefficient. So that filter coefficient also tends to be stable. Okay, so the bounded input will give you a bounded output. That's a good behaving filters. Okay. So again, those are computational details. The rest of that, more important is the idea is really centered around once you have this linear prediction model. What about it? What's the frequency interpretation about it, and how do we use it to do various estimation? Again, repeat the linear prediction model. Another way of thinking about it is they are all pole model. Okay, so a signal spectrum goes on filter multiplied by some input. Okay, the filter here is some gain, right? So we know it's just some energy within your error signal or the source. Okay, divided by AMC. AMC is the thing that we say, okay, this is linear predicted signal, the difference between original and the delayed version of yourself, right? CK tell you the delayed version multiplied by some alpha, sum it up. Okay, yourself with the difference between delayed and the delayed version of yourself. And then so we know this filter function is just a C divided by U of C, which is some gain, right? The energy, total energy divided by 1 minus sum from K from 1 to P alpha K C minus K, right? So we plug this in, right? Alpha 1, C minus 1, alpha 2, Z minus 2, alpha 3, Z minus 2. So this entire thing is a polynomial equation. This polynomial equation can be factored, okay, into a set of products. Okay, so those products will tell you, okay, at which position that individual product term will become 0. Okay, that becomes a pole in your Z plane. Okay, and everything happens in the denominator. So this is all pole model. Okay, so again, repeat. Okay. The all pole model is a linear time invariant system that depends only on input and the past inputs. Okay. In this linear prediction model is an all-pole model because we say the signal now is depending only on past P samples of input. Okay, it doesn't depend on the output. So what I have is an all-pole. So effectively, okay, you're designing an all-pole model. Again, these are interchangeable terms. Okay, keep your mind fresh, right? We start from linear prediction model. Okay, is their mathematical equations. We change it to the system analysis. Okay, we call it model. They are equivalent. Okay, having a time series model to say is a output equals a solely depend on its own past input. Okay, this kind of model. Okay, another term people like to call it an FIR filter, right? So those things only depend on input. Okay, these are OPAL model, FIR filter, or in this case we also say that linear prediction model. So they are all the same. Okay, they are all the same thing. It just depends on where you look at the problems, how you want to analyze them. If you analyze them as OPAL model, you're trying to analyze where the poles are, so you know in the frequency response of this particular filter, which position is going to have a peak. Okay, so that's keep this interchangeable terms in your mind. Okay, these are all the same. In a way, they are all the same term you have learned in different courses. Okay, so they are very. You just need to bring up, look at the mathematical terms. They are the same. Now the first question, right? How do we choose P, right? How many peak samples we look back? To make sure that the correlational structure are enough to capture, what's happening. Okay. So it depends primarily on sampling rate. Of course, if the sampling rate is very high, you might want to look back more points. Okay. If it's low, you don't have to look back as many points. So the P also means the order, right? The order needs to be large enough. Right, because you can remember the source and filter model. Okay, the filter part has this peak formants. Okay, so each formant there's a peak. Okay, every formant there's a peak in the spectrogram. That means if you're designing a filter, okay, it requires a pair of complex conjugate pole, okay, to model a single frequency peak in your frequency, right? So you can recall back in your memory of a signal system or DSP, okay, designing filters, looking at the Z transform domain, right? So your Z can be factors into those products. The product will have complex and conjugate pair. Each pair corresponds to one frequency peak. So every format, okay, we require to model a speech signal will require complex and conjugate pole, okay, to model that. So you need at least every format you want to form one format two. So every format you want to have at least two poles. You also need additional poles to try to model the spectral tilts of the entire spectrum. So usually, approximately, you want a P to be on the order of 2 times the number of formants plus 2 or 3. And we know how many formants do we have? There's Fs, which is the sampling rate divided by 2 divided by average formant spacing. Okay, so your formant, the first resonant frequency, the second resonant frequency, there's some average spacing. Okay. Average spacing, okay, it relates to the speed of the sound and also the length of vocal track. So approximately, okay, 1 per 1,000 hertz for male will be a formant. Okay. 1 per 1,000 hertz for 1 per 1,500 hertz, there will be another formant, okay, for female. So it depends on how many formant, okay, you want to actually model. So how many peaks does your linear prediction model alpha need to have, okay, to be able to model the spectrum that you want to look at. Okay, we'll show some plots later. So keep this in mind, right? We're again relating this very abstract concept of retransform, pole filter design to the actual speech signal that we're trying to model. And speech signal, the way we model because of source and filter, okay, exciting a resonant structure that creates formant, okay. The fundamental frequency on those high oscillation points, okay, those are fundamental frequency harmonics, okay. We're trying to use LPC to model the formant structure, okay. That formant structure, every formant, because they're peak in a spectrogram, we requires in your OPAL model, which is a linear prediction model, those alpha coefficient to have at least a complex conjugate pole to be able to model a single peak. Okay? And also the overall spectrogram has a little shape because they're peak here, the other peak here, but they are not the same height. Okay, those differences you require additional pole try to model them. How many do you need? It relate back to how we human vocal tract. The length of the human vocal tract will change the number of formant. Okay. Between the spacing of the formant, okay, between any sound. So you can approximate using this kind of formula to decide what the P. All right. Choosing the N, that's different stuff, right? So choosing P is a number of sample going back to able to predict current, right? So you get a short segment of window that's N. Okay, so wanna say, okay, decide how do we choose N? N, of course, is the length of the analysis segment, right? Your short time autocorrelation function, right? That N is there. Within that, you say I can run LPC. Okay, every single frame I look at past P samples. That P is because of the format. Okay. The N, okay, usually there are two different criteria to look at. One is you don't want it to be very large, okay, because when it's very large, then it's very hard to do LPC analysis within that segment because there's just many samples to do things. Okay, so you want it to be short to reduce computation. You want it to long to include each period to have reliable estimate. Good number, 10 to 40 millisecond, right? Again, if it's like when we talk about Fourier analysis, right? You want wide analysis or narrow band analysis. A wide band analysis, that means short narrow band analysis. You want to have a longer time to sort of include enough each period to have reliable estimate of the frequency inside that short segment. Good number, always 10 to 40 milliseconds or so. So again, across all this, right, time domain, frequency domain, down to LPC, we'll talk about other transform. This starting point is always this short segment. Okay, the short segment, that short segment is always between 10 to 40 milliseconds. And really the reason is because of the pitch. Okay, because of how many pitch you want to get within a segment so that you kind of have a reliable estimate. So okay, so another thing we want to talk about is the frequency interpretation of LPC model. So again, repeat in a back here the equation, right? Solving all those is using the Rickenberg equation you get is alpha, right? So you effectively design the edge of Z, okay, which is 1 over A of Z, okay, which right then is this one 1 minus all this summation, which we now know what alpha K are. Okay, so this is a Z transform of a particular filter. Okay, that Z transform of a delay filter, right? If you look at this, right, do your Z inverse in your mind. It's just delay 1 point, delay 2 point, delay 3 point multiply, right? So this is what we call the FIR filter. You have just designed with the filter coefficients alpha K, where you solve this autocorrelation function. Now you have designed the filter represented as Z transform as this. Okay, now we're trying to understand this particular filter, the frequency interpretation of this filter, right? So how do we do that? You basically say, okay, if I take Z, which is a complex variable, and you evaluate around the e to the j omega, so around the unit circle, that's where the frequency are going to reside. So that gives us the frequency response of this filter. Then we can analyze the frequency response of this particular filter. Okay. So even that LPC filter, H of Z, right? So we take Z complex variable and then say, okay, let's plug in e to the j omega to get the frequency response. We call it H to the e to the j omega. All right, let's look at the entire formulation again. So we know N of M error signal of a particular frame equals Sn of M, this signal segment minus this predicted signal, right? So we call this error signal. Okay, let's take the Z transform the error signal. Okay, E and Z. Okay, this is just S and Z, and this is one minus this thing. So that equals to S of Z, A to Z, which is we call it error spectrum, right? This is the error signal. This is the error spectrum. Okay, error signal's energy. The thing we want to minimize, which is this thing's energy, right? So we know energy conservation. Okay, Parseval's theorem. The energy in here is the same energy. So the Parseval theorem tells us the energy, right, in the error signal, which is the summation of n, En square n equals 1 over 2 pi over a 2 pi range of your transform En j omega squared e omega. Okay, so this is just Parseval's exercise. Okay, so the energy in the time domain equals the energy over a single period. Okay, within your frequency domain, they should be equal. So the energy no loss of energy as you do Fourier transform. This thing conserves convert convert it to the energy form here, okay? Called energy conservation. So now we know h of e to the j omega equals to g divided by a to the e to the j omega. Okay, so we know the error's energy, okay, equals to g divided by 2 pi, right? 1 over 2 pi. Now we have the form of g minus pi 2 pi. What's a of z equals Sn e to the j omega squared divided by h e to the j omega squared d omega. Okay, what's this? This is the signal's Fourier transform. Okay, this is your filter's Fourier transform. Okay. So in the whole optimization, what we're doing, we're minimizing this, right? We're trying to minimize this energy function to be able to get our alpha coefficient. So we're trying to minimize a ratio between the two. Okay, between your original signal's Fourier transform, its magnitude squared divided by the thing that you're trying to optimize for, which is your filter's coefficients frequency response, its magnitude to the square. So intuitively, by minimizing this, you will get those alpha coefficient to make sure this e to the j omega is going to track the peak of the filter of the original signal. Okay, because by tracking the peak of this original signal, this whole term will be small. Okay, so again, we're trying to in LPC define the error signal between the signal and the thing I'm trying to predict. Okay, I say the energy between the two needs to be minimized. The energy between the two needs to be minimized. This one. That energy in the time domain can be rewritten as a frequency domain. Okay, using partial theorem. Okay, so we have minus pi over pi the frequency the Fourier transform of the signal, original signal. This is the Fourier transform of the filter that you design. Okay. So by minimizing this, we're minimizing this. Okay. How do I make sure I get a set of alpha coefficients so that I minimize this? If my original Sn equals j omega in its spectrum has a certain peak, I want to make sure my h of e to the j omega has the same peak. Otherwise, this peak divided by this peak, okay, the ratio between the two, if I can model the peak well, then the ratio between the two will be small. Then I effectively will minimize the error signal's energy. Okay, so this is by design. Okay, this is by design. By minimizing the error signal's energy, okay, you effectively reduces h e to the e to the j omega to track the form of peaks. It works better when there's Sn e to the j omega is greater than h to the e to the j omega. Also, that means it tracks the spectral place better than the spectral value. Okay, so if your signal has some spectral value, okay, it doesn't track that as well because it doesn't contribute too much error at the value portion. Okay? But at the peak portion, that don't track it well, the energy of that will be blown up. Okay, let's look at it example. Think about here. Okay, that's an input signal, some speed signal at the very top. It's a time domain signal. This is a short time, short time Fourier spectrum. Okay, looks something like this. Okay, these are different orders of p. Okay, so the number of sample we look back to be able to track this. Okay, so if you look at p equals to 4, and then plot the h of z. H of e to the j omega's magnitude, you will look something like this. Why? Because if you look at this short time spectrum, if I only have 2 poles where I can place to make sure I overall minimize the difference between this thing divided by this thing, right? I want to find a set of alpha to minimize the thing I draw here and with respect to this thing. So my alpha will be placed around this position, so that it gives me a peak here because it tracks the peak here. Okay. If I place it anywhere else, it's going to give me a larger error. Okay, so you're placing your pole, okay, those alpha coefficients, which essentially are the pole location of your spectrum, placing their poles at the position where it actually tracks the peak here. Okay, so if you have more orders, that means more poles. Okay, more poles, that means you can track more peaks. Okay, you can start tracking, right? The second peak. The 3 peaks that you actually pick up, right? There's one around here. It thinks there's one around here. Okay, these 2 things are good enough. Okay, I have another one here to track this peak. Okay, so if you add more p to it, the thing gets more difficult to compute, but more spectral details you can actually get. Okay, so p equals 12, p equals 16, p equals 20, and more pole, you can actually use it to place on the e to the j omega, so that it has a certain frequency response. So yeah, p equals to 12. It looks like a very smooth version of original speed spectrum. Okay, so it captures what we call the filter part, right? All this wiggly stuff on the source part, right? So those are going to be left out in the error signal. Okay, so again, repeat, try to understand this process. And the thing I want to say is, this is by design, it's going to happen that way. Okay, it's not magic. Okay, it's because you say I want to have a linear prediction model. Okay? I want to say my signal is a linear combination of past p sample with a alpha weight. Those are my FIR filters. Then you say, okay, I want to make sure the error energy is minimized. Okay. Now by having these three things, okay, the alpha coefficient, the filter you're going to design is going to track, okay, the peak of the speed signal or that segment signal's peaking point, not the valley point. And the more p you have, okay, the more poles you have, the more peaks you can track. Okay. That's effective by design, and also, like I said, the want to minimize this, different. So if at the omega where the original signal has not a peak but more of a valley, it doesn't contribute too much to the error. So our filters won't be able to track those things that well, right? So if track them, then it doesn't really matter this thing. This is a spectral value. But the error between the two, yes, there's some error. But compared, if I do this right, okay, versus if I don't do this right, I will place my pole here, right? Then to make sure this thing divided by this thing will give me the smallest error. Okay, if I place if I try to track here, right, then the error will be evident in this range. Okay? So this is by design. Okay, the system will try to model a smooth version of your speed signal by tracking those formats, and that's why we say this is a trying to get the filter part of your speech production. If this thing excites by source, it'll become something like this, right? Because you have this and multiplied by a, say for example, some oscillating waves, then you have things like this. Okay, so keep this in mind. So we're flipping between different courses you have learned. Okay, but keep all this in mind. Filter design, Z transform, a linear prediction. Okay, autocorrelation function. Autocorrelation function are probably not. It's more learned like time response over mathematical codes. And these are system perspective of frequency analysis and filter perspective. Okay, so understanding the way you're designing LPC model, essentially there are a set of FIR filters. Okay, they are open models. The poles, the number of samples you look back, decide how many poles you have. The number of poles you have decide how many peaks you can track. Okay, and then those peaks that you track will give you a smooth representation of your spectrum. Okay, tells you the filter part of your vocal track. Okay, so you essentially can think about it. Another way to think about this probably is effectively you're decomposing the original short time spectrum as filter multiplied by something else, right? You're effectively decomposing this spectrum into this thing multiplied by the other thing. Okay, and whatever is that in this thing is called LPC filter. Okay, so again, larger P, you have more spectral tilt. In a good number of P's, you get Foreman spectral tilt. And usually these are, by practice, it depends on, again, number of sampling rate, number of pole, number of spectral tilt you're trying to model. Okay, we know the properties of the filter HOC. Let's look at the properties of the error, right? So again, we know alpha once we learn, okay, the error signal essentially is the input signal that we originally designed. Okay, so whatever is left not being modeled by the LPC model, that's error. The error is actually the original filter, the linear prediction model, that's source part, that the input part. Okay, So if LPC provide a good model of speech production, which is a filter, EN then provide a good model of excitation, right? So again, repeat, think about this. We formulate a model, okay, for this signal equals to its past P samples, okay, and whatever is not in there, okay. Now we design a particular methodology to get those alpha coefficients, okay. Now we know it's a good model, then whatever is not being modeled by that smooth formula structure, those are the excitation source, okay, whatever is left. And whatever is left is the error signal, and what we call is the source or excitation source, and we first formulate as an unification model, okay. So that's something. So Magnus error signal will be large at the onset of the pitch period because, right, again, repeat, the LPC model provides those peaks at formula location. Okay, whatever is left is the source. If it's a voice source, then that error signal will have peak related to the fundamental frequency of your original signal. So you can try to do pitch extraction on the error signal, okay, where the error signal essentially is the source, okay, of the speech production. Okay, and usually they are flat, okay, response because the formant has been removed and only demonstrate the harmonic structure will show up plot there. Right, think about this, right? This is the original short transpeach segment. It has this kind of oscillating harmonic structure with an overall shape of the spectrum. Now you say, I have a linear prediction model, there's the excitation source multiplied by a linear filter. And this is the filter you have learned. So whatever is left is always oscillation is happening. And those oscillation that's happening is your error signal. And those oscillation, of course, is because of your source excitation source, radiation, and so on and so forth. And because this thing has been removed, so in the error signal spectrum, you don't see these highs and downs. You only see oscillations. Okay, so we'll look at the actual plot. Okay, so these are just two different ways of doing covariance or autocorrelation. And this is the autocorrelation method. This is the correlation. This is the signal. Okay. Once you've done the LPC analysis, this is the error signal. Okay. The signal spectrum, taking the signal plot the FFT and plot it. Okay, you'll look something. You have this oscillation, but you have an overall shape, right? This smooth curve, okay, are the LPC filter coefficient. This rest of these oscillations are the error signals spectrum. Okay, so this thing multiplied by this thing equals to this thing that you see. Right, so effectively you're taking an LPC model to decompose the original this kind of oscillation with an overall shape into overall shape multiplied by this oscillation. Okay, and this oscillation are just there's some frequency here, multiples of these frequencies, right? These are fundamental frequencies and it's harmonics coming from your source. This is your filter. This is to multiply because of your speech signal. Okay, this error signal you'll see, it has a peak at relatively the same pitch period as your original signal and as your original segment of the speech signal. And these two are just different ways of looking of computing the same thing. You look at the some of the values are a bit different, but the overall shape is similar. So that's understanding of this. So you can think about having this model. You can start designing different somewhat of simple application you can think about, right? The first thing is saying, okay, if this is a good filter model, then give it a proper input. You can start generating speech sound, right? So LPC provides a very simple way of doing speech synthesis, right? So if I know it's a voice sound, input some pitch periods of 100 hertz, 200 hertz, do some impulse generator, okay? This voice sound that impulse generator becomes your U multiplied by some energy, right? Delay P different filters, right? And those filter coefficient are the LPC learning coefficient. Then you generate the synthetic speech sound, right? So again, because we have a model of speech production, source exciting filter. Okay. These are essentially your filter, FR filter. The source, if it's a voice, they have input, or if it's a non-voice, like sound, use white noise as your input multiplied by some energy, so make a it louder or make it less loud through these FR filters to have the speed synthesis. So again, LPC model provides a simple tool to start generating speech, okay, because you have effectively decomposed, okay, this speech spectrum as the filter part and the source part. Okay, the filter are ways we pronounce that sound, like at that sound, but to make it come out, you need to excite it. Okay, because it's a vowel, it's a voice sound, you excite it with a certain pitch period, because my pitch is lower, 50, 80 hertz, female maybe higher, 200 hertz, then you excite the same okay, then you can generate the sound. Okay, so in LPC model, repeat, we start by saying a sample is being linearly predicted by the P sample. Just this simple idea, okay, has many implication. Okay, the implication again, think about them in signal and system. Okay, this implication is basically trying to model the most informative sort of speech, sort of we call spectrum envelope. Okay, and leave the rest of the source into the error function. Okay, the error function can then be used as a input, or can be used as a way to do speech extraction and so on and so forth. Right, so speech extraction, we talk about speech. We can also do speech extraction here as well. Okay, so we can start to combine different methodology. Okay, so speech signal, say for example, it's on low pass filter, get rid of some noise, doing some downsampling. If I know my filter coefficient, the inverse of that, right? So HOC multiplied by SOC, HOC is a filter multiplied by the input equals my speech sound, right? So if I take my speech sound multiplied by the inverse of HOC, okay, it will become my source. So what's inverse of that is just AOC, okay, that filter. So that inverse filter that we have designed, so originally HOC is 1 over AZ, okay. Take that AZ, multiply directly to the speech sound, then you get this inverse filter. Then you generate, right? You generate output which is related to your source signal. Okay, then we know if the source or the error signal has the same pitch period as your original signal, how do I find that period? Okay, we learned back in time domain processing. To find a period in a time domain signal, what we can do autocorrelation. Then we do another autocorrelation on the error signal. Then you find a peak. Then you say, okay, that's your fundamental frequency. Now, think about it. Start piecing together things we've learned. Okay, time domain processing, we know the speech signal. If you want to find a pitch, okay, find a fundamental frequency, you can do autocorrelation function. Okay, find the lag that gives the largest value. Okay, because we know autocorrelation function itself has the same period as your original signal. Okay, here the same idea, but the front end, we do a lot of linear prediction analysis. We get rid of some high noise. Okay, do some downsampling and say, okay, if I know my linear prediction filter, okay, take the inverse of that, basically reciprocal. Okay, take the inverse of that, multiply to the original signal, meaning you do a convolution to your original signal. By applying those inverse filter coefficients, then you get error signal. Okay, and we know that because LPC provide a good representation of the filter. So whatever is left in the error signal corresponds to the source. And we know that error signal has the same approximate period, okay, as your original signal speech. Okay. Now what we need to do is find the period now in this time domain signal, which is an error signal output from the LPC analysis. How do I find the period of this Y event? Okay, we can find autocorrelation function on this Y event. We know the autocorrelation function itself has the same period as this, and also a cleaner, okay, version of this thing. Then try to do peak picking. Once you've done the autocorrelation function, then you do find a pitch period. Okay, so why bother doing all these things, right? Because it gives you a cleaner, right? It gives you a cleaner signal to do pitch period, right? Originally, autocorrelation function is directly operated on this time signal. So you try to shift this and then try to find the dot product to find the lag that's the largest. Now instead of doing this directly on this, you say let's do LPC analysis and find this so that I can find the error signal. There's also a peak here. Then do autocorrelation function to try to find the pitch period between the two. So this sometimes can be cleaner than this one. Okay, because we'll see all the rest of them because you have removed this thing. So essentially, you have effectively removed this kind of up and down variation. Okay, whatever is left now is just there's a signal here, then there's a pitch period here that you can just find this that correspond to all these peaks in your spectrum. So taking the autocorrelation function on this gives you an even more reliable estimate on a pitch period of the original signal compared to autocorrelation function directly with this signal. So it's a combination of techniques. Okay, we start to combine to design different speech technology, and then you'll see this thing continues. Okay, for people that are in the space of trying to estimate good pitch, okay, there are all sorts of techniques they combine to make sure an idea I can extract effectively these peaks from the speech spectrum without other things to interfere with my computation. Okay, so I want to start a little bit on captural analysis, and we'll stop there. Okay, so again, slowly moving. Okay, we have time domain. Okay, we have frequency domain. Okay, now we have a model that can be interpreted from time domain, can be interpreted from frequency domain, and also can learn, okay, or can derive as a minimization of some error signals, okay, to get those coefficients. Okay, so let's slowly progress to this point. Okay, and at the LPC model, you can start to realize, okay, when this kind of speech analysis tool really builds upon source and filter, and try to make sure we have a good model of either source or filter so that I can decompose the two. Because filter really tells us how the sound sounds like. Filter tells me, filter tells me what the sound sounds like. Source tells me who that person is. Okay, so if I can decompose these two, I can have either cleaner filter reliable estimate so that I can generate speech or can do speech recognition, or if I'm in the process of doing speech compression, speech coding, that's the part where I want to make sure that it maintains well, because that's where we understand the speech. Okay, filter part is the part we understand the speech. So the LPC model structure provide us in a tool to do that. And then captural analysis is another set of analysis that again help us to do that thing as well from a completely different angle. Okay, into the mathematical process. Okay, we'll talk about that quickly on the motivation, and then we'll get up early today. Okay. So the topic to captural analysis to cover. We'll talk about what is captural analysis. Okay. Specifically, in the captural analysis, the idea is really the homomorphic filtering. Okay, and the homomorphic filtering is basically the idea of using complex log within a particular filtering process. Okay, then we'll talk about what is actually a complex or the real captural with a definition. And of course, like Fourier transform, you never implement everything in continuous space. So it's always a discrete version of this. So how can you use DFT as a way to implement complex captural? So we'll talk about captural analysis of speech and then application of captural analysis. And later you can see that we can combine linear prediction analysis and captural analysis. Okay, then we have linear prediction captural coefficients. Okay, so then we can start combining different mathematical tools and then definitions and computations and applications of those things. Okay, that's motivation. Let's take a step back. Okay, so if you have a signal yn equals xn plus a signal, some low frequency, plus some noise, which is high frequency. Okay. If you take Fourier transform on this, this is low frequency. This is some high frequency noise. This is the actual signal that you record. If you do a Fourier transform on a spectrum, okay, because the signal spectrum and noise spectrums are additive, okay, then in the frequency domain they are separate, linear, right? Because the low frequency component of signal will be moved to the low frequency beats. The high frequency noise will move to the high frequency noise side, right? So you have a high frequency versus low frequency, and you added it, those two things. Take a Fourier transform. It's going to move the low frequency to the front of the coefficient, right? Front of the frequency beats. High frequency to the higher side of the frequency beats. Okay, so again, there's a power of frequency analysis. But if you have things like this, Yn, so output signal, it goes to Xn convolving with Un. Okay, this is some high frequency signal. This is some low frequency signal. So signal is low frequency convolving with noise high frequency. Can we find a transform domain such that make them become nearly combined or nearly separable? Okay. In this case, it's easy, right? Take a Fourier transform. The low frequency goes to low frequency. That's how we design low pass filter, high pass filter, right? Because basically in the frequency domain, it's low passive or high passive. Those at the original signal time domain, they are added. In the frequency domain, they are separate. Now imagine a case where in the original signal they are convolved. Okay, where Yn, Xn, low frequency, Un, high frequency, they are convolved. Can we find a new domain such that they are also separate? So I can take them separate apart. Okay, so that's the idea of analysis, trying to find capsule analysis that try to find a capsule domain. Okay, that's that does that. Okay. I think I told somebody already. I said the capsule, right? There's no real word called capsule. It's a swap SSC. Okay, spectrum. If you change SSC, it's spectrum. Okay, so and then in the capsule, the unit, the axis is called Q frequency. Okay, in spectrum, okay, the unit axis is called frequency, right? The Q and the F are being swapped. Okay, so it's basically it's a play on the word. Okay, there's no real word called capsule. No real word called Q frequency. Okay, but there's a new transform domain that we take it so that in that particular domain, these things can be sort of linearly separate. Okay, just keep that in mind. And why we want to do this? If you look at this equation, this is the whole time we've been talking about this, right? Source exciting filter, source exciting filter. Okay, that's a speed signal we want to get at. So we can find a new domain. These two things are separate. Then we can operate them separately. Okay, to do the things we want to do. In LPC, that's what we do, right? We say, okay, yeah, they're like this. Okay, but I'm gonna formulate it as a open model linear prediction analysis, trying to find what this filter coefficient are. Then I can separate this out. Okay. Now there's other set of analysis we want to try to do to separate. Can we find, instead of doing a filter design to separate this out, can we, instead of finding like a transform domain, okay, doing some transformation so that these two things can be separated out. Okay. So, but the idea always come from speech signal is source exciting filter. Okay. And this is higher frequency, it's lower frequency. Okay, so I want to make sure the idea is clear before we can move on. Okay, one thing I think about this, right? In this domain, right, in this frequency domain, if you think that there are two signals that adds that multiply each other, this is a there's a fast oscillating signal, okay, with a slow varying signal here. Okay, so you can find a domain that can separate the fast oscillating thing with the small or the low oscillating thing. Okay, then you'll be able to find a domain that's these two part, right? So we'll see that. So you take a Fourier transform and effectively you do like another Fourier transform, like 2 times Fourier transform to be able to separate, this oscillating thing, which is fast, okay, to this thing, which is a low oscillating thing. Okay, so we'll talk about that later, but I'll come back to the linearization, and then before we do all that, there's a set of chronology. I think it would be nice to know. It's an important concept. We won't cover every aspect of this thing, but it's important to know the background of capsule analysis is effectively coming from the idea of homomorphic filtering. So again, linear system we know is simplifies simple superposition. Okay, they are homomorphic to addition. Okay, so linear system, say if you have a signal that linearly combine the two. Okay, if you have a linear system, you can operate on individual component and then sum it up at the end. Okay, so it simplifies the process we do things. We call them homomorphic to addition. So linear filtering is straightforward. You can apply to each component, right? X of n goes through a linear filter, y of n, then well, that's the linear filter operated on input. So if your signal is a linear combination of the two, if you have a linear system, you can operate on individual one of them, and then you simply sum it up, that'll be the same thing. That's a linear system. Okay, so in terms of speech signal, they are linear, they're not linear, right? They're a convolution between excitation and vocal tract. Okay, so we want to have a generalized superposition, okay, not linear superposition. Okay, so x of n through some filters, y of n, h of n. If x of n equals to x1 convolving with x2, can we find a set of H filtering? No, that can operate on individual one of them. Okay, it'll have the same effect as though I operate on the entire term. Okay, so we're gonna find a set of generalized superposition. Okay, not the linear superposition. To the way we analyze the speech signal, because speech signal they are not linear addition, they are convolution. Okay, so we can find a transform, a operation, something that can individually operate on these two things, then we're done. This idea is quite simple, right? So we have again x of n, y of n through some filter h of n. Okay. So we can have x, right, goes, which is x1 convolving with x2, go through some d, okay, to get an x hat of n. The x hat of n equals x1 of n plus x2. Then you can say I operate a linear system on this thing. You get y of n, okay, which is y1 tilde plus y2 tilde. Then do an inverse of this transformation. Okay, then you back to yn, which is yn y1 convolving y2. Okay, so you can write the original linear system of input of some system, okay, output. If it follows the generalized superposition, that means if it's a convolution between the two, as though it is a yn equals to output of individual convolution output. Okay, you can write that as this thing. This is a general superposition. And how we do that is very simple. You say, okay, I just need somehow a transformation here that take this thing into a summation. Okay, then I take this take the superposition and do things and then carry on so on. Okay, so x equals x1 of z, x2 to z. So x prime has to be equal to x prime z plus x prime 2 of z. So we call this D is called a characteristic system for homomorphic deconvolution. Okay, so the idea is trying to convert convolution to addition, right? This convolution to addition, and this x hat of n we call them complex capstrom. Okay, so within the complex capstrom domain, things become linearly superposition. Okay, then we can just come back to the original time domain, and it follows a generalized superposition idea. So we just need to know what this sort of characteristic function is. So we can think about this as a transformation function that takes the signal originally as convolution from multiplication. All right. So what we say is basically is a log of the spectrum. That's fairly easy. So this is a system. Take a z transform and take a complex log. So first you take into the spectrum and becomes a multiplication, right? X and z multiplied by x2z, okay, in the z domain. Now, how do you break this multiplication into a summation? Okay, just take the log. Okay, take a complex log of respect to the z factors, then you get the addition. Okay, so log of x of z equals x hat of z. So log of x of z, right, equals the log of the real part plus the I to the base part, right? Or log of the magnitude of z plus the argument of z. Or you can write them as log of x squared plus y squared plus I arctangent squared yx. So different ways of taking the log on z, because z is a complex variable. Okay, taking a log on a complex function, it has a real part, imaginary part, a real part, imaginary part. But this log part, okay, effectively help you to take the original domain of convolution into a domain of addition. And into a domain of addition, then you can apply a linear system onto this signal and operate whatever you want. And then you come back to the original signal. And then this particular function is the log of the the Z spectrum of the original signal, and that's the Castron coefficient. Okay, so I'll stop here. I want to show what is effectively what we're trying to do here. Let's just speed signals spectrum, right? You always have this kind of oscillation, okay? We call it a slow variation of the envelope, okay? And the fast variation, which are the pulse-impulse trains, right? At the time domain, they evolve because they are source and filter model. At the Z domain or the J omega domain, they multiply. So you have this thing multiplied and C equals, basically you have this excitation responses, fundamental frequency is harmonic, which is the fast spectral variation multiplied by a vocal tract responses. This is like the LPC kind of filter kind of thing, right? You have these two things multiplied, get your HSP signal. If you have a system that want to operate on this, okay, these things are not teasable. Okay, these things are multiplied. So how do I tease this apart? Okay, so in terms of this homomorphic filtering idea, then we just need to apply a log. Why you apply a log, right? Log of this thing. The log of this thing will break this multiplication into a summation. Okay, so you have a log of this energy, log of this the excitation source. The log essentially just basically shrink this value, right? In terms of numerical operation, it's just things get smaller, right? So log of e to the scale, e to omega plus the log of the filter part, which is this thing. Okay. Then what we can do is then take this thing and then further do a Fourier transform. Okay. Do another transform because now you're back in the problem. Think about if this is a time domain signal. Let's don't think about it. Think about this as a time domain signal. Okay. Not frequency. Time domain signal, you have something that's highly oscillating plus something that's slowly oscillating. You want to separate these two. Okay. Designing some low pass filter. What you do, you take the Fourier transform on this side. Right, so this slow varying thing will move to what we call the front for the low Q frequency part. Okay. The high oscillation thing will be moved to the higher part, okay, called a high Q frequency, right? High Q frequency portion of things. Then what you can do is if you're more interested in this thing, then you just get rid of this kind of a low Q frequency pass filter, right? This part, okay. We don't say those are filter, we call them lifter. Why? Because FNL, right? So it's all the display with words. Lifter, you lift this part out, okay, then we get this thing, right? If you lift this part out, if you lift this part out, you get this thing. If you lift this part out, you get like your source filter, okay, source part of the signal. So again, repeat. We'll study more about this Castro analysis. This is precursor to the very diagnosed MFCC, right? Mel scale Castro coefficient. Okay, that's basically this set of coefficients. Okay, the idea really comes from about the knowledge we know about speech production, source exciting filter. Okay, now the knowledge we know about the homomorphic filtering. I say if there is a particular characteristic function or some function that we can apply on a signal, it makes the original convolution become complex summation. Okay. If I can do that, then I have a methodology to make sure that I can find a new domain that these two things are separable. Okay. And the reason why these two things need to be separable because one is about your impulses, excitation, pulses, train that excites the whole vocal tract. Another is actually your vocal tract. Okay. So if I can make sure this multiplication in a spectrum domain, convolution in time domain, becomes summation, okay, basically by taking a log, and this thing becomes a summation. Now we're back in the same problem of thinking about this time domain. Time domain signal has some fast oscillating signal with a high low oscillating signal. Find another transform, right? So Z transform, Fourier transform, whatever. Find another transform on this domain so that it moves the high oscillating thing to the upper portions of the x-axis, right? The lower oscillation to a lower portion of this axis. We call this Q frequency. If you take time to spectrum, then we call this frequency. Okay, it's the same thing. Okay, so we can effectively decompose this thing so that we have a catch-all analysis of the original signal. Okay, so that's a basic motivation. Okay, we'll go through a little bit more detailed computation, and then later you'll see it has many applications, right? Look at this, right? Your sort. So this oscillation will have pitch periods that's similar to your original speech signal. So you can do Castro analysis to pitch extraction. Okay. Then you can have this thing, okay, to estimate the filter coefficient. Do Castro analysis to estimate the filter because you do an inverse on this segment to get this set. So you know your former frequency and you will run this. So by doing a Castro analysis, by taking which portions of the parts of your frequency axis, you can either tells you the source properties or the filter properties. Okay, and then later we can also design ways to combine LPC to this Castro analysis. Okay, that's how we derive LPCC. Okay, so that's like, you know, again, before MLCC, people use LPCC. Then later people use MLCC. Okay, because LPC coefficients are more related to how we understand speech production. MLCC we'll talk about. It has the same backbone mathematical tools, but it comes from the inspiration of how we human perceive speech. Okay, it's a bit different from the LPC. We'll talk about that later, but make sure this knowledge is crystal clear. Okay, we haven't changed our source and filter model. Okay, from the very beginning, the first class speech production, source and filter model, always about source and filter model. Whatever methodology analysis tool that we design around speech signal is about understanding the source part or filter part. It's just that methodologies become more and more advanced. And then in terms of ASR, right, in terms of speech recognition, what we really want is a good representation of this filter, so that I can know, okay, each distinct sound differently. Okay, so if I plot R into this frequency and look at the frequency response versus E, and I look at the coefficient here of frequency response, it should be completely different. Okay, and that's how we utilize this coefficient as our features to do kind of a speech recognition from it. Okay, that's kind of a basic idea. So we'll slowly build upon that. Okay, 那我们今天先讲到这边。